All right. I'm happy to see you guys. I'm happy there are a lot of people here. Still, it's the last talk of these 2 days. 2 days very busy. So I'm pretty happy to be here. 10th year anniversary. So we hope to share something interesting for you. If you have a question and you don't understand something, just raise your hand. Let's try to make it a bit more like interactive. So that's the research we did, me, Federico, and Jonathan, and a few other colleagues. You see on screen, a big group. We all work for Trend Micro Research. So the idea was to look into the security of industrial protocols that are used, for example, in cranes, as well as a bunch of other machineries, like drillers, in the automotive sector, logistics sectors, everywhere. So radio controllers, like this one you see on screen. All right, so these radio controllers have been around for many years. So we made a kind of survey of different vendors, and we figured out that they've been around for 25, 30 years. You see, like, from the old controllers up in the 90s to the most recent one that have joystick and so on. So how these controllers are made of a receiver, like this one you see here on screen, which is pretty much a photo of this gentleman down here. So the receiver is made to be connected to the machine you want to make remote enabled. So you can connect it to any machine you want. And the receiver, of course, receives command from the transmitter. That's very simple. Huh? So the transmitter, you have one like this one. Maybe you can circulate it here in the audience, the first line, so people can give it a try. There are different buttons. And you can operate, of course, the machine that is connected to the receiver. We have transmitter like this one that have just buttons, while we have modern one that have joystick, but they're pretty much similar to each other. They're used, as I said, in different situations. They're used in a horse crane like this, inside big factories. They're used in construction sites, for example, to move like concrete pumps around, or to move, if you want, like cars, like big trucks, and so on. As well as what's called auto crane, that are used in, for example, in logistics, to move things around, and so on and so forth. So a lot of different applications, going from mining, you can see here, drillers, you can see it in industrial application, logistics, to move containers, agriculture, so on and so forth. So given the extension of this radio controller, we said, okay, let's take a look at those ones. You know, that seems to be like an important asset for our economy. So let's see if there are any potential risks. All right, so to do that, we start with what we call preliminary on-site testing, or if you want, war driving. So what we did, we went with Federico. We both live near Milan, north of Italy. So we went with his car, small like, what is it, like a small Fiat, but you know, we basically, we had like antennas, you know, as typical war driving activities. We have our war driving kit here, made of a laptop, software-defined radio, 2 of them actually. For those one that know about software-defined radio, one is a Blader F, the other one is a Etus. And yeah, we did a bit of testing around, visiting different facilities, factories, as well as construction sites, and so on and so forth. Overall, in something like a few weeks, we came across something like 7 different vendors being used widely in all these facilities. We have vendors from Taiwan, very much prevalent, some vendors from Italy, of course. Then there is one from Japan and one from Germany. And we took a look at the website of these vendors. They distribute globally, worldwide. So we thought it was a good set of vendors to look at, because they cover all different main nations in the world, from China to US, Europe. So we had a good testing set, if you want. As I said, we used the software-defined radio for that. I'm not going much in detail into this. I guess you guys most likely know what they are. It's a standard technology to implement radios via software, the computer. Very easy to use. There are different models that go from $100 to 500 and so on. And so we started by developing a small code in a form of GNU Radio flowchart. GNU Radio is a software that's widely used to implement software-defined radios. So you can see that we have a code on the left that allows us to record. So we can record a radio signal, record some traffic that is streamed over the radio, over the air. So we have our software-defined radio, and we dump the content that comes from here into a file. Then here we have the flowchart that actually reply such traffic. So it reads from the file, and it transmits over the air. Okay, so it's very simple. It's like you have a microphone here on the left, and you have a speaker on the right. All right, so we did our preliminary on-site testing, and can you guess what happened? I'm going to show you a small video here. So as you can see here on screen, that's exactly the flow chart I showed you before. So this is me talking with the operator on the other side while he's smoking a cigarette. I'm there with my hands in my jeans, and I have a radio controller here. So this is one of the radio controllers I was showing before. We have Federico in the car. Federico is going to reply a packet that we collect previously. As you can see here, that's a big crane. And you have a big crane moving, like this, easily. Then we did a second test. We went to a facility where they rent auto crane, so a crane on an auto. Here is the same. That's my laptop. I run the script. That's a Blader F. Connect to my laptop. That's the original transmitter. Nobody's touching it. And you will see soon what will happen here to the auto crane. Moving up. All right. So let's describe a bit here where is the problem. So this is very simple, and I'm going to describe to you why this is happening. So suppose you have a transmitter that want to send a command like up. Like in the example of the auto crane, move the auto crane up. So what the transmitter does, he encodes this command into a message, transmit the message over the air, message number 1. The message arrives to the receiver, this one. What the receiver does is decode the message and they execute the command. Very simple. If the transmitter sends another command, let's say the same command, up again, what the transmitter does is generate another message called message number 2, send the message over there, the message arrives to the receiver, and so on and so forth. So if I want to send multiple commands, up, I'm going to generate multiple messages. So the first question to you guys is, for this radio protocol to be secure, how these messages should look like? Yeah, Marcus?
Yes, there should be a different message for the same payload per transmission. So there should be something like rolling code or whatever to change to prevent replay.
Perfect. So the answer was this message should be different. Even if you are transmitting the same message, they should all look different. Because if they don't look different, what an attacker can do, can record the first message, can reply the first message as message number 2, and of course the receiver will execute the command. And of course this is not the case, so we test all the vendors here, and all the vendors were vulnerable to this very simple attack because all the messages were the same. So this is called recorder reply attack. Is one of the main attacks that we will go and describe during this presentation. So as I said, you can record here a command and reply the command. So I will now make a small demo to show you how this attack is performing in reality against our fake crane down here. So this is the transmitter, is off. Just put it here. This is our Blader F connected to the laptop. So we switch here. I execute. Can you see, guys? There is not much to see anyhow because it's like this. So what the Blader F will do, will record a message that I previously recorded before the talk about moving on the right, and the crane will operate as a consequence. Stop. All right, but what about if attacker is more smart, is more intelligent? So you want to do more than this, because this is very simple, no? So suppose you have your garage opener, and instead of replying the same message, opening only your garage, I'm going to open all the garage. So what about if I understand how the packet is created and I want to modify that? So this allows to do arbitrary code execution. So to do that, as I said, the attacker has to understand how the radio protocol is made, what is in the packet, in the radio packet. So to do that, he has to do, of course, reverse engineering. No? So as you have a sample, you have a binary sample, you want to understand what the binary sample does, you reverse engineer your binary sample, for example, to figure out if it's a malware or not. Here it's the same, use a reverse engineering technique, so there are techniques to reverse engineer radio protocol to understand how the protocol looks like. So if there is a checksum, how the checksum looks like, if there is a sync code or not. So in that case, what an attacker can do, can understand how the checksum is made of, and what he can do consequently can, for example, replace the command up that move the auto crane, up, to a command that could be like, could simulate an emergence. So all this transmitter, they have a button here on the top. So the operator, in case there is an emergency, like a problem, he can stop immediately the machine, the crane, by pushing this button down, like this. Of course, the attacker can do that. He can record any arbitrary message. He can then reply the message, but a modified version of the message. So he's going to reply the up command with the emergence stop command. He will compute the correct checksum for the command and send it, but not once. He will send it once, twice, 3 times. So it will basically cause denial of service of a production. So what does it mean? It means that you have an attacker that is sit outside of a factory with a small equipment like this. It can block the production, block the crane, block any kind of logistic communication, and so on. So we have a demo for this as well. So do you mind passing the transmitter to someone here in the room? So here we have a small script that implements what I previously said. So what he will do, he will send multiple emergence stop commands. So at that point, what will happen is that the crane will stop operating, even if the operator wants to move the crane.
Even, but you see the LEDs there, they will stay consistently off, right? Even if I'm trying to restart those safety relays, there's no way I can use the crane anymore, right? Maybe for small intervals, but then it goes off again. So now it's still off.
Okay,
right?
Let me stop this. All right. So this looks pretty easy on paper, but might not be necessarily the things. So I'm going to now we are going all together to dig into the domain of reverse engineering a radio protocol. So how it looks like, where you should start. So you should start by purchasing the device you want to target, of course. So in our case, is this gentleman here. The mark is Juuko And this is with the cover, this is without the cover, and is actually the gentleman down there. And you have, of course, the transmitter. So what you're going to do, you're going to open it up, figuring out how it's made. If there is an MCU, how many MCU there are, if there is a radio chipset, which kind of radio chipset there are. So in this case, there was this radio chipset here, CC1120. This is the original one with a kind of cage made by producer, Juuko. You take out the cage, you understand how the chipset is made of, the type of chipset that runs. At that point, you can look at the datasheet, try to figure out how it's connected with the MCU. So you figure out the different pins on the board and so on and so forth, and try to understand how the communication looks like. You can start tackling the radio protocol by doing reverse engineering of a signal. So this is a tool called URH, Unified Radio Hacker. It's a tool that allows you to look into protocol, radio protocol. So here you have the signal that is transmitting over here. And if you're smart enough, you can see that there are 4 different lines here. So each line is actually a different frequency that the transmitter uses to communicate a different symbol. So since you have 4 of them, you can understand that there are, the symbols might be, for example, 11, 10, 0001. Another thing you can point out is that in the first part here of a packet, only 2 layers or 2 frequencies are used, or 2 symbols if you want. While on the rest of the packet, there are 4 symbols that are used. So this already gives you an idea of which kind of modulation has been chosen by who developed the firmware of this device. Of course, this seems, again, easy, but it's not really easy. So now Jonathan will dig a bit deeper into this domain and what a smart reverse engineer can do to figure out how the signal is made of.
So if anyone has kind of worked with SDRs at this level, I mean, it can be very challenging, right? And you can get into situations where very quickly where you're looking at signals, but you really don't have any confirmation that what you've decoded or that what you're looking at is correct. And you may have to go through lots of different iterations and testing and trials to kind of understand that you're on the right path. And it's easy to take wrong paths, right? Is this noise? Is this data? Does this look right? When it's all correct, it will work. But if something is just slightly wrong, it won't, right? So what are some other techniques we can use, right? And as mentioned, many times radio chips are used, and lots of times they have simple serial interfaces like SPI and others. And it makes sense that anything that can happen on the radio, any state, any messages transmitted and received, anything like this is transmitted over SPI, right? So if you can instrument SPI, you can always know the radio state, right? Combine this with the fact that you can, of course, find data sheets for these parts, and you can look at the SPI registers, and you can see that, again, all the configuration information is stored conveniently in registers, right? So, again, comparing that to reversing RF at the signal level, this gives you very precise information about what frequency the radio is tuned to, what sync words are being used, what deviation amount for FSK would be used, what kind of modulations are being used, right? So if you can instrument at this level, you can save yourself some time, right? So we created a tool, right? We took a logic analyzer, we took raw waveforms, we converted them to SPI, right? We looked at the register reads and writes. But as you can imagine, if you're kind of doing the kind of research we were with many different devices, many different buttons, you have many different states that you want to examine, you might want to look at what happens when the device boots. Is there a pairing sequence? Is there crypto exchange? What happens when the device is idle? We saw things like heartbeats and stuff. So ultimately, you have to do lots of analysis, and reading SPI reads and writes, at this level, of course, can be very tedious, right? And so these are some examples of our kind of first layer of tooling, right? You can see these are addresses and these are data, but staring at this all day is going to get very tedious, right? So what do you do, right? Well, luckily, again, in the data sheets, all the registers are there, right? And you can literally cut and paste all the names and make references to these registers in order to assist your decoding, right? And then once you have register names, then you can kind of build a system that's easier to read and easier to use, right? But still, even with names, you have hundreds of registers or thousands of register accesses, and so it can be challenging, right? So again, at this level, this is an example of when we applied some more decoding. Just even if you don't know anything about this radio, you can kind of intuit that, oh, it's reading signal strength, something is happening with the radio, it's going idle, it's looking for the number of received bytes, it's actually reading the bytes, et cetera, right? So this would be easily identified as a receive loop, right? But again, you're going to still be digging through many accesses. So what we decided to do is create an emulator, right? So we take this streaming set of SPI operations and we emulate the register states that are described in the data sheet. And of course, default values for registers are also described in the data sheets. So you know kind of the initial conditions that you need to apply to your emulator, right? And this is important because even between revisions of silicon and things like this, default states can change, meaning if a certain firmware is run on the same chip but a different revision, you can get slightly different behaviors. But we accounted for that by looking into the data sheets to find these defaults. And of course, dumping the state at any point is really key, right? And again, this helps us to get to the point we want to be, which is what are the parameters of this signal at the time of transmission or reception or any other point, right? So you can set triggers in this process, and when you have a transmission, you can dump the state, right? So this is an example of kind of what our emulator dump looked like. You can see the configurations, the various radio signal parameters are all captured here, right? Here we have the values, the number of reads that were performed and writes, so you can kind of get an idea of how the software is working, if certain registers are being accessed or if they're not, and things like that, right? So we also, we had the expertise to work in the SDR field, so we created GNU radio blocks to emulate the protocols that we were interested in. This is just kind of an example. And one thing we like to do also is to use stuff like ZMQ to be able to push messages in and out from other Python and modules and other tools, right? So, and this is kind of an example of the types of messages we would take, right? It's just a simple Python dictionary where it says, we want the preamble to be A's, we want the sync word to be this, we want the address field to be this, and the payload, we want it to transmit, et cetera, right? So it's kind of a pretty simple interface, but it allows you more interactivity with more tools from GNU Radio. So we plug this all together, right? And ultimately what we have now with all of this assembled together is we can process waveforms off the SPI bus, put them into our emulator, create messages during transmit and reception, pass those messages into GNU Radio, and have an actual signal over the air, right? So literally you could attach probes to a physical device and have a companion software radio acting just like the target radio you're analyzing. So one of the key benefits of this is, since it's all in software, now you can instrument it at any layer. If your modulation isn't correct, or you're having some problems, or you want to look deeper into how protocol is working, again, you have all this software in front of you, and then you can instrument it and inspect, debug, change. And at this point, too, we had kind of a global team with limited devices, so I did a lot of this work from logs and SPI captures and data sheets, and I never actually touched a device during the process of building the emulator. So this is just a really simple example. There's some logs and triggers, and we instantiate the emulator, and it runs until the transmit and just breaks. And this is a more complicated view. I realize it's hard to read, but it's kind of there for reference. But this is a set of standard GNU radio blocks that I use in order to recreate the radio, with the exception of a couple ones. We have some specific decoding which is done for the protocol. And then GNU radio also didn't have a pre-canned way of demodulating for FSK, so we implemented this as well. And then Fede is going to talk a little bit more about the reversing process.
Thank you, Jonathan. Hi, everyone. So, if you paid enough attention, we haven't told you how we figured the payload structure yet. We told you we figured it out. We told you we could figure out the CRC and, but we haven't told you how we did it. All we knew at this point in time was that we had the CC1120, which is not very different from the CC1101, but enough different to make it very, very difficult to use the 1101 for talking to the 1120. And using Jonathan's emulator, we were able to find out what was the configuration of the radio before the transmission. So we could tell, among the other things, that, for example, if you open the data sheet, you can tell that it's using standard packet format. So that's already some good news, right? But still, what we really want to figure out is what's in there. Because this CRC is not the CRC that Marco was talking about. This is a CRC that is inserted automatically by the transmitter, right? And it's calculated on the data field, on the length, address, and sync word, if they're used, right? And it's removed in transmission. When it's received. And this was one of the things that caused some trouble. I remember that we were replying with the radio, we were replying basically the SPI logs, right? The data that was pushed onto the transmission FIFO, and we wouldn't see any activity on the radio. The receiver would not pick it up. So we tried multiple times. Maybe the strength is not enough. Maybe we're missing something. The preamble is not right. We tried everything. And then at some point, we looked at the data sheet and say, oh, it's removed by the receiver and inserted automatically in transmission. So that's why we don't see it on the SPI, right? What you send on the SPI is basically just the data and the address and the length, right? And then the radio will, package it nicely with a preamble and all the rest and just transmit it. So, how do we figure out this? Because this is the important part. This is where the vendor has done customization. This is where the vendor have hopefully baked in some security or try to, do stuff and make sure that the protocol is obscure enough that nobody will have enough time to reverse it and figure it out, right? But we had enough time. So we started by looking at the same transmission for the same command, right, over time. And we noticed something that you may say, oh, this is just a payload. You may say, oh, but this looks like a rolling code, right? You see the first byte, right? It's rolling, it's counting up. And then the rest of the data looks kind of different all the time. It is different all the time. So we kind of were, okay, wait. Reply attack is working, but the packets are all different. And then I see a progressive number as the first field. What's going on here? Is it rolling code? Is it not rolling code, right? So we took long captures, like we, just shorted all the switches and kept the logic analyzer attached to the bus for like minutes until we exhausted the search space, basically, of this first byte, until we got all the, FF numbers. And then we decided to do the opposite, right? We noticed that if we sort all the payloads that we got for all the commands and keep the first byte fixed, we also noticed that something else is remaining fixed. Not really everything. Like, you see there are some differences here, but you see that there are 4 bytes here that are kind of interesting, right? So we isolated that the first byte was sequential, right? But we could kind of find versions, so to speak, of the same commands, right? So we were going somewhere. The clicker is not going anywhere. Marcus? Okay, so those 4 bytes looked interesting, right? They look interesting because if we go back and we open up the cage and we look in the back of the receiver or the transmitter here, we find something that reads 201077 C8. So maybe it's a pairing code. Maybe it's 4 byte. I mean, it's written 1 raw with no separators, but it looks like 4 bytes of stuff, right? And it's constant, right? Sort of constant with the same, let's call it sequential ID or seed, okay? So we reconfigured the transmitter and the receiver. They have USB ports. You can reprogram the pairing code, just in case you want to, change your password every week in your crane controller or industrial controller. You can change the pairing code on both receiver and transmitter. So we left one of them set to the default one. And since we don't know anything about crypto, I don't know anything about crypto, I set the other one to 0. Right? I did the same. We did the same thing on another receiver and transmitter, and we set everything to 0. Let's see what happens, right? Let's see if we can figure out something. If we XOR the same packets with the same sequential ID taken in onto 2 different configurations, you see that you can unmask basically the pairing code. If you know how this might be called, please tell me, because I don't know it. I mean, we couldn't figure out. It looks like a shift register something if you look at all the payload, but we couldn't figure out a name. So we found out that the remaining 4 bytes are pairing code, encrypted or obfuscated with some rolling mechanism of some sort. There's an error in the slides. What says pairing code? It's actually the command. Because if you look there, in the remaining 4 bytes, what you have is, did you notice the 0, 1 somewhere? Okay. We found that every time we were pressing button X1, look at this column here, every time we were pressing X1, we would see 0, 1 here, except for those, but we were confused by these as well. But we found out that these were heartbeat signals that every once in a while the transmitter would send. So that's our 0 command, right? Then there is the 1 command. Then if you go around, you enumerate all of them, you find out that in that position, if you XOR 0, 1, 0, 2, 0, 3, 0, 4, and so on, you get all of the commands selectively. So you can write your own packets, basically. So this gives us, I wouldn't call it a different attack. It's more like a different attack primitive. Like, we could re-implement all of the attacks that we have shown before, including the DOS and so on, using this command injection primitive, which is a little more, fine and selective. So once you have 1 packet or no packets and the pairing code, you can figure out what the packet can be, and you can forge your own commands. Luckily, this device, as I said, transmits heartbeat signals every 2 seconds, right? So you get, very easily, you can capture 1 packet. That's all you need, right? You are in the range, you get 1 packet, you can forge every other packet, okay? You create a sort of a rainbow table, so to speak. So we re-implemented the e-stop abuse, and re-implemented another attack that we haven't spoken about it yet. Very briefly, these devices, some vendors offer what is called repairing mechanism, that let's say that you want to have 2 crane operators or 2 machine operators with 2 different and independent transmitters paired to the same to the same receiver. You don't want to climb up the crane and do, repairing of everything, right? They offer a so-called pairing mechanism by which, pushing proper buttons, you can put both of them in pairing mode, right? And then you push a certain sequence on the transmitter, and it will send a sort of a seed, right, to complete the repairing, right? Some vendors do it right, in the sense that they have physical buttons on both, so you really have to be there if you want to start the pairing procedure. Other vendors all you have to do is to be there within the first 4 minutes from the boot, and the receiver will accept pairing packets. So you can either forge or replay a pairing packet, and you hijack. If you want, you can even kick out the previous receiver because you can, send a different pairing code, right? So the legitimate operator won't be able to use their code anymore. Sorry, their transmitter anymore. If we want to step up a little bit and introduce another type of attackers, if you think of a state-sponsored level kind of attacks, these devices, as I said before, come with a USB port. The reason is you want to be able to refresh the firmware. If you send it into maintenance to the system integrator, the system integrator might be able to reconfigure it. Some vendor even sell a tablet with the software for configuring these devices directly to the client. So the client can purchase the USB dongle, the iPad or whatever, or a computer, pre-configured to change all the parameters. And the parameters can be, I don't know, I want to reconfigure the mapping of the buttons, I want to change the frequency slightly because I want to avoid interferences, I can change the pairing code. So these are getting more and more flexible, right? And the vendor is giving out some of this flexibility as an added value to the market. And people want it. I mean, if they didn't want them, then they wouldn't sell tablets pre-configured for reconfiguring these devices, right? So you can think that there might be some places in this supply chain where either one machine is compromised or one machine is malicious, right, and is trying to interfere with the flashing procedure. So what we did is we wanted to assess to what extent this would be possible. So for all the vendors that we have looked at into our lab, we purchased also these dongles. And we spent some time with this saga. My colleague Philip, he's not here, he's from the Taipei office. He spent quite a lot of time on this. And what we did basically is we initiated the pairing procedure, the configuration procedure from the software. And we were able to intercept, you just you tap into the UART, basically, use logic analyzer, then you decode the protocol. You know what the MCU is. In this case was a MSP 430, it's fairly popular. There's a simple bootloader, and then there is a password, right, which usually is used to protect from reading the firmware, but you can also protect it from writing the firmware, right? And then on top of that, you can do complex stuff at the firmware level, such as integrity check verification. You want to make sure that, nobody can read your intellectual property. We found out that if you look at here, there's a NAK, NAK. We tried to supply the wrong password, right, that we were able to intercept during the initial programming procedure. So they were sending the programming password in clear. And the second one, we tried with the right password, and then it responded with a NAK. So we were able to write firmware with no mass arrays protection. We were also able to read the firmware. We took a look at it with IDA, and we found out that the integrity check procedure was not supported by hardware. It was not supported by any form of even very weak and poorly implemented PKI. It was just an integrity function baked into the firmware itself. So I could write my own firmware that verifies its own validity. Okay? On top of that, even if you don't want to do all of this fancy stuff, the software that is used to reprogram these devices do not have any form of authentication. Right? So if you don't want to do fancy stuff, you can just you can use auto IT to automate the clicking on a compromised computer, and you can reprogram the device without any kind of authentications needed. There's no interaction. It's completely unattended. So yes, it is feasible to backdoor this firmware if you want, because the integrity is not guaranteed. So we have malicious reprogramming. Last part. If you were at the Armory booth, I've demoed a small dongle device I've put together, exactly because I wasn't able to figure out how to talk to the CC1101 to the CC1120 using the CC1101. But I want to introduce this topic from another angle, right? The angle is, what if the attacker is not within the range? What if the attacker is not able to stay within the 1 kilometer line of sight kind of range? Well, the barrier from SDR to radio dongles to, self-made device and things like that shows that it's going lower and lower and lower. So the threat model from this point of view is different than it was, for example, 10 years ago, probably when these devices were designed. So now, with very low investment, and if you want, very low effort, new attackers come into the scene. So, for example, you can create a device such as this with a 3G modem or with a 2G modem that will allow an attacker to be, local while being to the other side of the world, right? You put one transceiver on one side and another transceiver to the other side, and you can bridge the two, and then you can do fun stuff. I want to give you a short demo if you haven't had a chance to come to our booth. Meanwhile, if you have any questions that come to your mind now, feel free to ask. Marco is not here anymore. Okay, let's just put it on top. Okay. All right. So the experience is similar to RFCAT. If you're familiar with RFCAT, the idea of the tool is that the radio is modular. So you can change it. I've abstracted the details of the radio driver. And if you have ever used a CC 11 something chip, you know how painful it might be to talk to these devices. They have a very complex register settings. It's very difficult to figure out the right register settings. So I try to abstract most of it. And I'm trying to make it modular so that if you want to target another type of radio and you don't want to use the GNU radio, you can detach the module and attach the right module, and you should be kind of good to go. It comes in two versions. There's a serial version and the cellular version and the Wi-Fi version. So you can bridge it as you want, as you need. Okay. Okay, let me just reset it for. Okay. Okay, so now the dongle is telling me that it's set to the default setting and it's responding. Let's see. As Jonathan said, the registers, figuring out the register setting requires either guessing a lot, if you know the radio parameters, and then using Smart RF Studio to figure out the registers, or you tap into the SPI if you can, and then you know exactly what the values are. So I've made this already, so I will just copy and paste. What the dongle is doing now is setting the registers one after another. So now it's ready. Do you remember I told you before about the various commands? We figured out that if you XOR at a specific position, if you XOR the right value, you can obtain another command. All right, so now I'm going to turn on the transmitter. Okay, so I'm in a realistic scenario, so to speak, where in a construction site, the device is set there. Maybe no one is doing anything, right? I'm not lucky enough to be able to intercept the command that I want to forge. All I need is a heartbeat, right? So this guy now is transmitting an heartbeat. Of course, I could receive, but now I don't want to receive. All I want to do is to, anytime I see one packet, I modify it on the fly without going back and forth from the host to the dongle. Everything is happening on the dongle. I write a rule that says, look down here. Every time you see a packet, modify it, and at position 8, make a XOR of whatever is there with CMD. And CMD in this case is X1. So you can create various rules, X2, X3. You can create all of the library of commands that you want. Or, just to recreate the scenario that Marco showed before with the emergency stop, I can hang on, I haven't saved the estop command. I have to paste it. Okay, I'll just try again. So I'm going to tell the dongle that I want to have a packet modification rule, such as this one. So every time I see a packet, insert at position 7, the value that is there, XORed with estop. And then I set it to repeat mode. Repeat mode is nice, because every time it sees a packet, it changes the packet and retransmits it right away. So it's perfect to create interactive protocols, and it's kind of efficient because everything happens on the dongle. So now it's in denial of service already, and I'm trying to restart it, but there's no way. Even if I keep the start button pressed, kind of works, but doesn't. Because every time it sees one packet, it's going to burst 5 packets, or how many packets you want to retransmit, changed the way you told it. And of course, I can create my database of command once I know the packets. So I can do I can restart it and then do, I don't know, x1 n times, something like that. Okay? So, where were we at? Okay. This is probably the part that most of you would like to hear about. So we saved the best for the last. We of course did a long responsible disclosure process. Long because you can imagine that some of these vendors might not be ready to hear what we had for them. Simply like it happens for the embedded world in general and for industrial systems. Vendors in this space might not know what we're talking about. But we had several mixed responses. Some of them said, oh, okay, here's the patch. I'll release it immediately. Some of them said, no, they didn't say anything. They never responded. Some of them responded and say, I will not fix it because it's by design. I want to keep it like this. Some of them said, oh, the product is end of life, right? So I don't want to support it. And the question here, how long is the life, like acceptable life for these products, right? 1 year, 2 years, 20 years? We found products on the field that were there for 20 years, right? What are the chances that they will get patched? Some vendors initially responded a little bit harshly. They said, maybe you should talk to our legal office because we're thinking about suing you. But then we kind of, found a way to talk to them, and at the end of the day, they patched. So great work from ZDI, our colleagues from Trend, that went through this pretty painful but successful disclosure problem. Problem. Freudian slips. Conclusions. So we found several patterns of vulnerabilities. All of them can be summarized under the umbrella of there's no encryption whatsoever. If there is a rolling code, because we can call it a rolling code, the one we saw before, it wasn't enforced at all. We were able to forge packet, so the receiver is not enforcing the rolling, the synchronization. There was no protection in the vendors that we have examined at the firmware level. And so we hope that, with this talk and similar talks, we'll be able to raise a little bit the bar. We're very happy that we were able to gain the attention of a standardization committee in Germany that said that they were using our work to push for an amendment in the requirement for these devices to be able to operate in real environments. In the same way, they have to have an emergency button. They should not be vulnerable to a reply attack. At least reply attack, right? That's a bare minimum to ask. So for vendors, you see, I shouldn't use this. For vendors, what we hope that we will see in the future is that they will use open and standard technologies. There are some vendors that use BLE, for instance. At least use rolling code, even though it's not secure, but at least these devices will be more secure than your garage door, or as secure of your garage door opener. Use some protection on the firmware, and make sure that you educate your users for maintaining them. And on the user side, we hope that they will be able to, promote vendors to, use updates and make sure that will apply. So with this, I think we should, all come back to stage for questions if you guys have any. If you're interested in details, we have 2 versions of the paper. We have the white paper by Trend Micro Research, and we have the academic paper that will be presented in June at DIMVA in Göteborg. If you're in Sweden, please make sure you come. Thank you very much.
Thank you.
Thank you so much for your presentation. Are there any questions?
Here.
Yes.
Marcus. It's going to be a super technical question.
Yes.
No,
Sure.
it won't be. Thanks for the great presentation, guys. My question is, I very much like the reversing approach on the SPI end. So my question is, you mentioned you had access to the firmware update process. Why didn't you approach it from the firmware end of the transmitter or receiver? Mm-hmm. There has to be some kind of controller, and you could get you didn't choose to take the possibility to have a look at the application layer. Mm-hmm. I guess it's easier to start from this end.
Philip did it. Our colleague Philip did it. Honestly, he managed to extract the firmware towards the, like 80% of this work. And he confirmed how the structure of the payload of that particular vendor was made. So we could confirm that. But not all vendors are, not leaving, not all vendors are leaving no protection on the device. So for this particular one, we couldn't extract the firmware easily, right? We couldn't interject the update procedure because we didn't have the firmware itself. All we had was the configuration tool, not the reprogramming tool, right? So it's a mixed situation. And also, ultimately, we wanted to show that there are multiple type of attackers. The attacker that can be, very physical, so to speak, on the device. The attacker can be just only radio. So we stressed a lot to make it just with radio at the beginning, and then we went into SPI, and then towards the end to the firmware level.
Yeah, and specifically in the protocols we looked at, the application layers, part of the payload, wasn't so complex that it wasn't obvious, right, or that we couldn't reverse it. Now, the one that that we spoke about with the XORs and keys, that one was a little bit more complicated, but we were able to get it without having to go through the process of reversing. But certainly, there's going to be situations where that will help, right?
Okay, are there any other questions? No? Then I would like to ask for a big round of applause again for these guys' presentation.
Thank you.